Good afternoon. My name is Dominique Sy from Salle University. Thank you for the opportunity to present my paper entitled Intergenerational Mobility in Industry 4.0. The paper is organized as follows. First, I'll discuss the introduction, the methodology, the results and discussion, and finally, the conclusion and recommendations. Let's begin with the introduction. The Philippine government has announced the Ambisyon Natin 2040, which is a 25-year development plan which encapsulates our vision for a middle-class society by 2040. Unfortunately, the numbers do not paint a good picture. The Philippines is vulnerable to novel technologies that include additive manufacturing, predictive analytics, and cloud computing. In fact, research has shown that over half of the manufacturing workers in the Philippines and other ASEAN countries may be displaced. Over 1 million jobs in the country may be eliminated. These include jobs in clerical work, wholesale and retail, and manual labor. And over 18 million jobs will be impacted, whether through reskilling or changes in responsibilities. All of these imply that there are new dynamics that challenge the classical theories of mobility, and our country is ill-equipped to face technological disruptions. Thus, it is crucial to examine how to best equip our nation's youth for the future of work. This brings us to our central research question. How are intergenerational transmissions affected by the rapid technological developments brought about by the Fourth Industrial Revolution? We have the following research objectives. First is to present an extended theoretical framework that marries classic mobility theory with technological change. Then, I present a novel task-based metric of automation susceptibility based on natural language processing and machine learning. And finally, this paper empirically examines the relationship between technology and mobility in the Philippines. This paper covers the years 2003 to 2018 of the Philippine Labor Force Survey, and it has the following limitations. There is a lack of longitudinal data to record parent-offspring outcomes over time and generations. Thus, this uses repeated cross-sections. Next, there's the prevalence of additional streams of income, proliferation of attenuation bias, and transitory effects, which could introduce significant bias in the study. Thus, it's important to use sample selection methods that provide stable estimates. And finally, there's no established metric to point estimate or compare mobility across subgroups. Thus, this paper uses the rank gradient measure, which was presented by Chetty et al. In his 2014 paper. This paper contributes to the research as follows. There are only few studies that have examined the link between technology and mobility. The Gowler and Sidon in 1997 did examine this, however, only theoretically. And in the Philippine context, there are numerous papers that have examined mobility and gender dynamics, as well as mobility and intergenerational income elasticity. However, none have examined the link between technology and mobility. Which brings us to the methodology section. This research uses the following main data sources. The principal data source is the Philippine Labor Force Survey from 2003 to 2018. This includes information on the daily basic pay, the educational attainment, the primary occupation, the kind of business, the nature of employment, and other characteristics of the members of a household. The primary occupation of an individual is then merged with the Philippine Standard Occupational Classification based on the latest edition, which is 2012, and older years are recoded. And the kind of business is merged with the PSIC, or the Philippine Standard Industrial Classification. This paper uses stringent inclusion criteria, such as permanent employment and an age restriction between 15 to 65, which is based on previous literature, which showed that this criteria produced more robust and stable estimates. And finally, it also uses survey-weighted estimations, which are based on the PSUs and final weights given by the Philippine Labor Force Survey. Now, how exactly do we characterize or estimate the link between technology and mobility? As mentioned, we are going to use a rank relationship between the child's skills versus a parent's skills. Now, since we're looking at the context of Industry 4.0, skill is now determined by the automation resilience of a certain individual. The way we measure this will be discussed further on in later parts of the study. And this is based on the copula of the bivariate distribution, as defined by Chetty et al., and it mitigates the effects of differences in marginal distributions between the two groups. And it's specified as follows. PS, or the probability of being skilled, is proxied by S rank, which is the percentile rank of automation resilience of the child, regressed against the locational fixed effects, the S rank of the parent, the A sub S, or the technology measure, as well as X, which is the vector of parent capital-based investments, and of course, epsilon, which is our error term. Now, how do we measure the technology parameter? This is the labor share of individuals who are employed in an advanced industry. These advanced industries are measured based on the Muro et al. Definition in 2015, and we simply divide this by the total number of employed individuals in the area at time t. Now, how exactly do we measure the automation resilience of an individual? So allow me to present a task-based metric, which is based on machine learning, wherein we input the occupational descriptions of a certain job by a certain individual into a machine learning algorithm, which will output a probability of automation based on the descriptions of the tasks that that occupation will perform. And on the left, we can see the pipeline of how exactly this will be performed. The very first step is we hand label a sample of occupations, which are at the unit group level. We assign them a tag of 0 or 1 based on whether they will be automated or not. This is based on Frey and Osborne's 2017 paper. And the reason why we use a sample is because there are only certain occupations, around 10%, that we are absolutely sure will either be automated or not automated. Then we transform these text inputs into numeric vectors using the NLTK package or Python. Then we perform several classifier algorithms such as the naive Bayes model, logistic regression, and random forests to train these models. Then we compare them with goodness of fit metrics to determine the model that we will use for our final estimation. Now, why do we have to use a machine learning based approach? With this, we are able to extract the features from the task descriptions in the absence of sophisticated databases like the OSTARnet, which the US has. The OSTARnet is able to have very explicit and very specific variables on the task content of a certain occupation, which we do not have. So we have to rely on this novel method. Also, we're able to avoid the issues in manually labeling the entire set of occupations rather than simply getting a sample and then using an algorithm to predict the probabilities for the rest of the occupations. And finally, we're able to assign actual probabilities of automation to each occupation based on the task content of that occupation. Now, how does feature extraction work? So in order to transform our text inputs into numeric outputs, we use count vectorization, which outputs a sparse matrix of binary variables, which are simply the counts of certain words in the document. Then we also use another method called the term frequency or inverse document frequency vectors, which are specified as follows. That we use naive Bayes, which is a simple probabilistic classifier. It assumes orthogonality among the features, and it maximizes the posterior probability, and it's specified as follows. We also use logistic regression, which predicts binary outcomes. It uses a latent function to map the probabilities between 0 and 1. We also use random forest classification, which is a classical machine learning algorithm. It's composed of several decision trees, not as prone to overfitting, and it's calculated as follows. Now, once we actually ran these different models and combinations of the feature extraction that we did, we found that the naive Bayes classification with word level TF-IDF was the best performing model, followed by the logistic regression with count vectorization and the random forest with word-level TF-IDF. Then we use the ensembling method to combine these top 3 models to form the final trained model that we will use in order to reduce bias and overfitting. Finally, we use this trained model to classify the rest of the text inputs that we have, and we are able to arrive at certain probability values for each unit level classification. We then aggregate these unit level classifications into the sub-major group level, which is then merged with our main dataset, which is the Philippine Labor Force Survey. Now let us discuss the results. This figure shows the automation probability of certain classes of occupations in the Philippine Standard Occupational Corpus. Now, this shows us that occupations under operators and assemblers, such as and crafts and related trades workers, are more likely to be automated than other occupations. Now, this follows what we would expect because these occupations tend to be more manual and repetitive in nature, whereas occupations that are on the left side of the spectrum, which are less automatable, such as managers and professionals, are those that require more, say, more skill or more social capital, so to speak, and are less likely to be automated. Now, we examine the regional trends in susceptibility to automation. So a lower number indicates that that region or for that year is less likely to be automated. And we can clearly see that NCR, or the National Capital Region, is less likely to be automated than other regions. Whereas regions like Region 1 or Region 2, which are more agriculturally based regions, are more likely to be susceptible to automation. Finally, we look at the intergenerational transmissions of skill using these simple transition probability matrices for father-son, father-daughter, mother-son, and mother-daughter pairs. The principal or main diagonal for each table shows the level of persistence across skill quartile. So it's divided into 4 quartiles, which are highly resilient, moderately resilient, mildly resilient, and not resilient, which is based on the automation probability that we got earlier. From here, we can clearly see that skilled pairs display very strong persistence. In fact, 80% of skilled mothers raise skilled sons, and 70% of skilled fathers raise skilled sons. Now, this follows the proposition that we see in the literature that the odds ratios below 1 with offspring from less skilled households definitely having worse odds of transitioning to a skilled occupation. And here we see the actual estimates of the regression model that we proposed earlier using linear regression with fixed effects. And here are the repeated cross-sectional results based on 3 different specifications. First is the base model, next is the base model with a technology measure, and finally is the full model with the controls. We can see that parental skill rank is strongly and positively associated with the child's skill rank. And this is more apparent for sons rather than daughters. And the effects are significantly moderated after adding controls. Now, what can we conclude and recommend from these findings? We were able to accomplish our objectives of presenting a new theoretical framework and implementing a task-based metric that is based on natural language processing to measure automation susceptibility. We were also able to empirically assess that theoretical model and the task-based metric through Philippine data with proper sample selection and robust estimation. Rebuild, reskill, and reinvent. First, rebuild. We need to shore up on digital readiness by developing ICT infrastructure. We also have to implement public-private partnerships. Next, reskill. It is crucial to nurture the development of skills for the digital economy. This may include subsidies and programs for upskilling, such as the Sparta program. We also need to have support for parents and children who are undergoing distance or remote learning during the pandemic. Finally, reinvent. The country needs to have more interoperability across systems and also involve itself in regional cooperation for the sharing of best practices from our neighbors. We also need to promote greater transparency and open access to data, as well as the creation of a national longitudinal dataset similar to the US in order to better study long-run dynamics. And that's the end of my paper. Thank you very much.